So this next video is going to be about the reverse from exponential growth. This is going to be about exponential decay. But the good news is both exponential growth and exponential decay, they both use the exact same formula, PERT, the same formula we used in the first video. The only difference is when you're talking about exponential decay, the future values will be smaller than your starting value, and your growth rate will be negative instead of positive. That should seem pretty reasonable, and negative growth means decay. That should be pretty understandable. When you are talking about decay, though, there are some vocabulary words that are new and need some explanation. In particular, I really need to explain the word half-life. Most people have heard the word somewhere before, but they may not know what it actually means. So let me draw you a little picture of what that means. So there is some sort of a starting amount, remember, and we're going to be decaying over time. The half-life is the length of time it takes to get to half of however much you started from. So let's say that's say p over 2. So it's the length of time to go from the starting amount to the final amount. And here's where most people go wrong. They usually get this part just fine, they understand it, no problem. But in their mind, they imagine the graph looking wrong. They think the graph is going to look something like this. So by the time you get to, let's see, what's double that? 11,460? That it'll be down at 0. But that's a straight line. Remember, this is exponential decay. It doesn't drop like that. What happens instead is, in 5,730 years, the half-life means it will cut any starting amount in half. So if your starting amount is here, in an additional 5,730 years, it'll cut that in half. So we had half to begin with, and then half again. And half of a half, you know what that is, that's a quarter. And then in another 5,730 years, let's see, 17,190, is that right? Yeah, 17,190. It'll be half again, so it'll be down at the original amount over 8. So the curve is leveling off. You've got that asymptote behavior. And this is actually why radioactive materials are such a problem. In half-life, it drops by half, but then it's not going to drop to 0. It'll still be at a quarter, and then an eighth, and then a 16th, and maybe eventually the amount will be small enough that it's not a problem anymore. But it takes a lot longer to get to a really small amount than most people think. Most people think it drops linearly, and that's not actually how it works. So in this problem here, you got to keep in mind, that's what half-life means. It's not going to be just a straight line after that. We have to use that purple formula. Okay, now, once we know what the vocabulary means, the actual process of doing the computations here, it's luckily really similar to what we did with exponential growth. Step 1, just like it was with exponential growth, step 1 is find R. Figure out what the growth rate is. In this case, the decay rate. Figure out what the decay rate is. And it's not going to be 5,730. That's half-life. That's not the same as a rate. So what we're going to do is, like what we did in the previous video, we're going to plug in everything that we know something about. So take your formula, A equals P e to the RT, and here's what we're going to do. We're going to plug in the half-life. We're going to take 5,730 and we're going to plug it in for T. So we're going to have e to the R times 5,730. And here's one of the funny things about exponential growth and decay. We don't actually know the starting amount. I mean, read through that paragraph. carbon-14 is a radioactive isotope that has a half-life of... It doesn't ever say what the original starting amount was. But even though we don't know what P is, we do know at that point in time we have half of the starting amount. This may look like an unsolvable equation to you. I mean, if you have a good sort of big picture understanding of the structure of algebra, you're looking at this equation and you're saying, but there's two variables in there. I have R and I also have P. How can I possibly solve an equation that has more than one variable? Well, the good news is our very first step is to divide by P. And it cancels out on both sides. You have P over 2 divided by P is just 1/2 equals e to the 5,730R. So really, you don't have to know the starting amount if you know what the half-life is. Any starting amount will get cut in half in that length of time. So, get rid of the coefficient by dividing by it, and you're down to a single variable. Move the base to the other side, turn it into a logarithm. And then divide by the 5,730, and you've got your decay rate. So, for this substance, the decay rate is, grab the calculator, natural log of 1/2 divided by 5,730 is negative 0.00012096809 etc. When we start step 2, I'm not going to use that decimal. That decimal is a mess. And it's good to know that it exists, and it did come out negative, which means it is decreasing like we expected. And it's a very small decay rate, which means this thing takes a really long time to decay away. 5,730 years for a half-life is a pretty long time. So this is a reasonable decimal to get, but I actually kind of like this version better. This is easier to work with in my equation. So there's your step 1. Step 2, just like we did last time, is use R in the formula to answer the question. So in the formula, A equals PE to the RT, I'm going to use natural log of 1/2 over 5,730 for R. Now, what was the question? I've forgotten what it was. You've forgotten what it was. Let's scroll back up and see what the question was. The question was, how old is this piece of bark? And all we know about it is that it has lost 90% of its original carbon-14. So lost 90%. Started with an unknown amount. Lost 90% means it has 10% left. So the current amount is 10% of whatever it started with. Here's what that means in the equation. The current amount is 10% of the starting amount. That doesn't seem like we have enough information to put it into the formula, but yeah, it certainly is. 10% of P. And what are we going to do with P? The same thing we did a second ago. Divide both sides by P. And then move the E to the other side, turn it into an exponential, and then get rid of this coefficient of T by dividing by it. Although here, it's probably easier to mentally do it in 2 steps. What I'm going to do is I'm going to take the 5,730 denominator, and I'm going to multiply it up to the other side, and then separately divide by the natural log of 1/2. That gives me something that's easier to put into the calculator. It's the same as dividing by the natural log of 1/2 over 5,730, but this is easier to type. So 5,730 times natural log of 0.10 divided by natural log of 1/2 equals 19034.0 6, 4, 7, 9, 8, etc. Did it say anything to round? I've forgotten. Let's see. No, it doesn't say anything about rounding. So if this was the real world and I was talking to a real person about this real number, I'd probably say something like about 19,000 years. But in a math class, where you're supposed to provide precise answers, I would say this. Okay? Or even this, if they don't give me something about decimals. There's going to be a third video here that's going to answer a very important question about half-life and exponential decay, and it will give you one more opportunity to see how using this formula PERT actually gets applied in practical situations.